All right, we're gonna get started. Thanks everyone for being here on a 2:50 p.m. Saturday afternoon. It's a very nice weather, so hope we get through this soon. My name is Ashish Kamra. I'm a senior manager at Red Hat, managing the AI performance team. And with me, I have
Samuel Monson. I'm a performance engineer on Ashish's team.
So we're going to talk about how do you run LLM inference performance benchmark on NVIDIA GPUs from soup to nuts, which I was recently told is an American only phrase. Someone from Australia didn't really understand what that meant. That was interesting. So the agenda for today is I will walk through the easy part of the slide deck, which is how to install a GPU driver on a Fedora instance in AWS. There are a lot of things I learned in the process of doing that, so I wanted to share some of them with you. And how to run a VLLM inference server using Podman. We'll unpack some of the nuances. Then Sam is going to dive a little bit deeper into inference benchmarking basics and the tool Guide LLM that we use for benchmarking purpose. It'll go through some of the metrics that you see as part of running a benchmark. What do they mean? And some extra bonus slides if we have time after that. Okay, so the first part is actually getting a GPU instance going. So I'm gonna show you how to do that on an AWS cloud. So this is my recommended way. Do not go to the AWS console and search for a Fedora AMI because you will not find it. So instead go to the Fedora project website and they have a nice link which leads to Azure, AWS and other clouds. And from there you can select a region on which you want to launch your GPU instance, and it will actually take you to the AWS console if you are logged in like I was, and it will find the Fedora image. You can see on the far right side, it actually loaded the right Fedora image that you can use. So in this case, I'm using a G6.xlarge GPU, GPU instance which has a single L4 GPU. So that's the easy part. It's pretty easy if you follow it this way. Yeah, you can launch the instance, and yeah, now you can SSH into the instance using the private key that you specified, and then some housekeeping, and then you reboot the node. Okay, so now the actual part of, so once you have the instance up and running, so these are the things you need to do. So it's pretty simple actually. So enable the RPM Fusion repos in Fedora, and both the free and the non-free ones. And yeah, the next command is just install the NVIDIA drivers. So we'll go a little bit more detail into what we are doing here. The AK mod NVIDIA package and the Xorg X11 driver NVIDIA CUDA package. So what's happening here is the auto kmod package is really useful for reinstalling the drivers after every kernel update. So it will rebuild the drivers for you so that you don't have to do that every time you move forward to a new kernel version, which happens very frequently in Fedora and other Linux distributions. So that's a really, really useful piece of package to be running in your system. And so this is really the driver that's maintained by the Fedora community. And it's the core driver and the basic CUDA toolkit that allows your user space AI applications, like we'll see later, VLLM, to talk to the NVIDIA driver. But this is not the full CUDA toolkit. So if you are developing new applications, you have to install other CUDA packages as well, but they're all available in the RPM Fusion and the non-Fusion repos. Okay, so once that happens and you have rebooted, so just check for the installation using the NVIDIA SMI binary that comes with the packages. So here you can see the output. There is a NVIDIA L4 GPU right here with 72 watts, a pretty low-powered one. Um, and yeah, so everything looks good. Now we want to actually run a VLLM server. So that's our AI application that will load a model and perform LLM inference. So for that, we have to install Podman first. But apparently, seems like Podman is already part of Fedora 42. So I'm just installing extra packages here. Remote and Compose, you probably don't need them. Um, and so this is the fun part. I really wanted to talk more about that. So after doing Podman installation, you have to install the NVIDIA Container Toolkit. So what you do for that is, yeah, again, enable the right repo, as I have shown here, and install the NVIDIA Container Toolkit packages. And um, so I just wanted to go under the covers of this a little bit more. Okay, and before I go there, you generate the CDI spec using the NVIDIA Container Toolkit. And then you can actually run any container and access NVIDIA GPUs from within that container. So the way I'm showing here is a sample podman run command that passes all NVIDIA GPUs to a Fedora container. So you might see the word Fedora there. And I run the NVIDIA SMI command inside the container. I'm just showing here that it will fail. It might fail when you try it with an SE Linux permission issue. And you can see that we don't have the container use devices capability, but while we are still passing the NVIDIA GPUs, so you just have to make that capability available, and then you're good, right? So now you can run NVIDIA SMI from within the Fedora container, like you can see here in this screenshot. But I just want to go a little bit under the cover of what exactly happened. But how am I able to access the NVIDIA SMI binary from a regular Fedora container, which obviously does not redistribute any of the CUDA user space stuff or any of the drivers? So the short answer is all the magic is taken care of by this thing called NVIDIA Container Toolkit behind the scenes, which injects the host GPU device nodes, right? We install the drivers and all the user space stack into the container when we specify podman run, -- devices, NVIDIA GPUs, all that support is there in Podman, also in Docker, to actually do all of this behind the scene, bind mount the right directories from the host into the container, so that everything is available in the container. So it's a pretty neat trick. So you don't really need to have anything on your container to actually be using the driver or run your GPU powered applications. Okay, so we have now a container in which we have NVIDIA SMI running. So now I'm just gonna show how to start a VLLM container. So really, there's nothing fancy to it. So you download the model from Hugging Face. So install the Hugging Face CLI, create a directory to download the model. So this is my workflow. You can bypass this. Sometimes you can just launch the model directly with the VLLM container, and it will download the model and cache it. But I like to have a separate folder for my models so I can arrange them nicely. So I'm just creating a separate folder on my host disk for the Llama 3.18b model, and just downloading the model to that folder from the Red Hat AI Hugging Face org. Yes, so this is kind of the final part of the process. So you now also pull the latest VLLM container. It's the latest one. When I tried it recently, is the 10.2, 0.10.2 version from Docker Hub, and now you can launch it the way I'm showing here. So I will unpack that command in the next slide for a bit. So what we are essentially doing here is podman run. Thanks. All right, I can take this. We're doing a podman run to launch the container, removing the container when we exit from it, giving it a name, um, passing the devices, GPU devices, and the CDI takes care of the things in the background. As I explained earlier, we are using the host inter-process communication so that all the shared memory is, like all the memory on the host is available for shared memory, mapping the ports between the host and the container, again, bind mounting the folder in which we downloaded the model into the container, also bind mounting the Hugging Face cache space in case we need that inside the container. So, and then yeah, just launch the VLLM container image that we had downloaded earlier and pass it the name of the model that we had downloaded and the max model length to kind of make sure that it fits within the small GPU that I'm using in this case. L4 GPU only has 24 gigs, and then the port. And that's it. I guess at this point you have a running VLLM container loading the Meta Llama 3.1 8B model. And with this, I will hand it over to Sam to talk more about what to do with this model and how do you benchmark it.
Thanks, Ashish. So yeah, like you mentioned, we now have a model. We're running it on our system as a server. So how do we kind of quantify what we have, if it will work for us? So we'll get into how you benchmark an LLM. In LLMs, the term benchmarking usually refers to two different things. There's performance benchmarking, which measures the throughput and latency of your system or your model output, while accuracy measures the quality of the model output. Optimizing a deployment often puts these two things in conflict. Moving from a smaller, more lightweight model to a bigger, more resource-expensive model will often improve accuracy at the expense of performance. Of course, like many things in life, one of the solutions to solve for both of these is to spend more on the problem. We get a three-way trade-off between accuracy, performance, and cost. Accuracy is a pretty deep topic, so in this presentation, we will be assuming that you've found a model that meets your accuracy requirements already, and we'll be focusing on optimizing the difference between performance and cost. Within performance, we care mainly about two different metric types, throughput and latency. Again, as with inference benchmarking as a whole, there's a trade-off in optimizing between these two, between high throughput and low latency. And just like before, often we can solve this by throwing more money at the problem. Thus, our goal will be to minimize our costs while meeting the expectations of performance in the other two areas. When trying to measure LLM performance, it's best to when trying to measure the performance of any system, it's best to break it down into atomic events and measure the latencies for each of those events. At a high level, LLMs follow a standard client-server architecture. So the atomic unit of work for client-server is a request. So we can measure request latency as the time to complete, we can measure latency as the time to complete a single request, or you can call it request latency. However, LLMs complicate this a bit. When looking at performance of something like a web server, we assume that each request and its response time are mostly homogeneous. You would expect identical requests to produce near identical responses and thus take a near identical amount of processing time. For many LLM use cases, these assumptions don't hold. Overlap between user queries can be quite minimal, and even when there is overlap, the responses from the LLM can be completely different. We need a metric that is consistent regardless of the request. It turns out LLMs have a smaller unit of work called a token. A token is basically a single word to an LLM. Some human words are tokens, but generally human words are split up into multiple tokens. We can ask the LLM to stream us back tokens as it generates them. Since our single request is now split up into these multiple events, we can define a new latency and new throughput metrics to account for requests of different length. Tokens are streamed back to a client one at a time in sequential order. The work done for each token is identical from the model's perspective. We can expect the latency for each token to be similar. An exception to this is the time between the start of the request and the first token, which includes extra work to queue and process the initial prompt. So we define two latency metrics for our token streams. Inter-token latency is the average time between each token, excluding the first token. And time to first token is the time between the start of the request and receiving the first token. We now know how to measure a single request, but that does not make for a very interesting and informative benchmark. So what we really want to know is how our server handles multiple requests. The simplest way to send multiple requests to a server is one at a time. This is what we call a synchronous benchmark. The next step up from that synchronous benchmark is a concurrent benchmark. This involves multiple streams of synchronous requests running in parallel. There are also other ways to handle parallel requests. One is to spawn them at a specified rate. This rate could be interpreted as a constant flow of 1 over however amount of time, or as an input for a distribution of requests over time. We can use one or a combination of these request patterns depending on the use case. We'll be using concurrent in this presentation as it's the more straightforward one to interpret results from. When benchmarking an LLM, the data set used to prompt the model has massive effect on performance. So for each benchmark, we must use a data set model to our intended use case. A data set can be as simple as a text file of prompts. However, for the sake of reproducibility, we also recommend defining the output token count for each of your prompts. In most cases, what really matters is the number of tokens rather than which tokens are used. So it is perfectly acceptable and often easier to generate random tokens for a random token data set for a use case. This is called synthetic data generation. Based on some analysis of popular use case data sets, we came up with a few prompt token counts which can apply to general use case categories, and you can see them here. Now we've gotten all the requisite knowledge out of the way, we can finally move on to running a benchmark. We will be using an LLM load testing tool called Guide LLM. Guide LLM may be installed to any Python environment of your choice and run as a CIL tool. Or, since we already are using containers, we can just download Guide LLM as a container image and run with that. This will be the option we're using for this presentation. So now let's run a benchmark. Running Guide LLM through Podman is pretty much as simple as just wrapping the normal Guide LLM command in your Podman run syntax. Arguments can either be specified as environment variables or as command line arguments. I have specified target here as both for illustrative purposes. Starting at the top, target points Guide LLM to VLM's HTTP server. Host containers internal is a special host name you can use in Podman to address the host system, as localhost might mean something different from within the container. Next, Guide LLM needs certain ports of the model locally available in order, certain parts of the model locally available in order to calculate how many tokens are sent to the model server. Processor needs to be set either to the model name on Hugging Face or a path to the locally installed model. The data flag is used to configure our data set. We want a synthetic data set where each prompt has 32 tokens and 32 tokens are requested from the model. To add a little more realism, we also specify a standard distribution of 8 tokens for both prompt and output. This will cause the token counts for our data set to follow a normal distribution centered on 32. It's a little more realistic than every request being the exact same length. Next, we configure our request pattern to be concurrent and configure a spread of concurrency levels. Guide LLM will run a separate sub-benchmark for each concurrency level and display all the results at the end. Finally, we set a stopping constraint of 10 seconds per concurrency. Guide LLM supports stopping the benchmark either by number of requests or by a set time. The default, if no constraints are set, is just to run through the whole data set once. Ignore random seed. We might touch on that later and why you'd set that. So now we'll go through a quick demo of the tool actually running. At the top, we've just specified the command we went over before. You'll see some things are configured, and then we start running benchmarks. During the benchmark, you'll get some live statistics of what's going on. These are inaccurate, but give you a good idea of if it's actually sending requests, what generally are the times. As soon as we finish a benchmark, we'll move on to the next benchmark and progress through that. And then at the end, I'm going to skip forward a little bit. We will get this large blob of information. This is split into 3 main sections. Benchmark metadata shows the input config and overall info of the benchmark. Benchmark info lists per benchmark info, duration, how many requests were made, average token counts, etc. Benchmark stats is the main section we care about. It lists many of our metrics: measured requests per second, concurrency, output or total token throughputs, and other various latency metrics. This, plus even more data, is written to the JSON output listed at the bottom. While it's possible to interpret the results from this page, it's a little easier to figure them out if you're graphing them. So here's a few graphs I'd recommend starting with. Output tokens per second versus concurrency can help you detect any anomalies in your results. These two values should scale linearly, at least until you peak out on your throughput. Any token latency versus output tokens per second shows you your performance trade-off that we were discussing earlier. For latency, you always want to use a high percentile value for comparison. Here we are using 99th percentile, which tells us that 99% of our requests had a latency lower than these numbers, or equal to or lower than these numbers. If your results are too noisy, though, you might need to drop down your percentile to 95th or even lower. You have your results now. Now, how do you classify performance with them? First, you need to set some objectives for your system. For example, I could require that my TTFT be no more than 1 second, while my ITL could be no more than 50 millisecond. Secondly, you need to look for the first inflection point in your latency versus throughput graph. This is where latency starts increasing faster than throughput. This usually indicates the point at which your server is overloaded and is starting to queue work on its side. You should try to avoid targeting a throughput beyond that point, as your system will not be able to maintain it long term. Now look at the highest throughput given those two constraints. Does it meet the requirement of your use case? If yes, good, you've found a working system for you. If no, you'll have to adjust the components of your system. Anything from tuning VLM's options to splurging for better hardware. That's pretty much it for running the benchmark. Now we'll just go over a few things that you might run into while running your benchmarks, and some things just to keep in mind doing that. First off, you need to run your test long enough to stabilize. A good ballpark is the time it takes to complete at least 2 times the number of concurrent requests that you're trying to run. So if your request concurrency is 50, you want to make sure your benchmark completes at least 100 requests. At lower values, you might even want to go higher than that, but I'd say generally it's like this gives you enough information, especially at the medium to high concurrencies, anywhere between the 50s to the 100,000 range. This is a good value to follow. Run the benchmark as close to the server as possible. You might be tempted to measure from where the client would actually be, as that's a more realistic scenario. That's good for realism. It's really bad for reproducibility, though. You can't rely on that network being the same the next time you rerun the benchmark or even during the benchmark. So it's best to measure it next to the server and then separately measure the latency between your server and your client and add that to your calculations. Tailor the data set to your use case. I kind of touched on this earlier, but all the metrics can be pretty highly dependent on the prompt token counts, and even some are dependent on the output token counts. If you have 2 different use cases, or you have a use case, 2 different things, or like completely different patterns for your requests, you should run them separately and get results for each. There's also some complications. These are like features that a lot of model servers have that might get in the way of your benchmark results being good. The first is batching controls. So VLM supports 2, maybe more. These are the 2 main ones we have to play with. Max num sequences limits the number of requests that we'll even try to process at a time. So if you send more than this, whatever this is set to, you will not get, your request will just automatically dump to a queue. You'll see that, basically, that latency spike that we talked about earlier, if this happens. So potentially you are leaving performance on the table that your model server could, if it's large enough, could handle more. Num match batch or max num batch tokens is pretty much the same thing, but for the number of tokens in all of your requests. So you just have to increase both of these and test again and see if that helps with your overall performance. The next thing is prefix caching. Prefix caching is a great feature for improving the throughput of your system. It essentially, when you send a request, it will try to cache the beginning of that request, and when you send another request, it will try to reuse the calculations done for that request, which is great if you're sending exactly the pattern that you would get in a real-world scenario. But if you're randomly generating requests, or if you run a test that's too small, the whole thing is cached, rerun that test, you will get way better numbers your second time around, will completely throw off your benchmark. Either turn it off or use some controls around the generation of the data set to tune your prefix caching hit rate. That's why we set the seed earlier. Those tests were run at way too small of a number of requests, and so we cached basically the whole thing and had to rerun it with that. The final thing I want to cover is speculative decoding. If you have really good latency, but you're not quite hitting your throughput targets, you can enable this. It's a little more finicky than the other ones, which are mostly plug and play. Speculative decoding, you basically have to put another model in front of your bigger model, which will try to predict ahead of the bigger model. This will sacrifice latency, obviously, because it's essentially another layer you're running through. But it can improve your performance. So that's something you can try. However, you need to tune your data set specifically to speculative decoding because it needs to actually be able to predict accurately. If it fails to predict, then you are obviously never going to get any hits on this speculation, and it will just be terrible. So here's a few benchmarking plus kind of things we didn't cover in this presentation. There's a few different ways of using AI. One which is pretty common these days is multi-turn, which is actually interacting with the AI rather than just sending a request and getting a response back. What this means in practice, though, is all you're really doing is you're sending a request, getting a response back, sending a completely new request with the history of your previous request included. So when benchmarking for it, there's kind of two ways of doing it. If you don't have prefix caching and you don't have any of these fancy features enabled, it's pretty simple. You kind of just can make a data set that has both these tiny little requests that would be the initial request and these bigger and bigger requests as it goes on. However, that won't work for any caching or any built-in system for the model server to kind of detect that it's already seen this information. Instead, you need to have a tool that supports multi-turn and can basically send the request and append what it gets back to the next wave of requests. LLM doesn't have support for this yet, but it will in the future. The second thing is vision language models. A lot of the assumptions we make on tokens being the atomic unit is that a token is a token. It always performs pretty much the same in any scenario. You're doing the same math no matter what. For vision language, which is models that support both images or videos and also text, that assumption doesn't hold because you can have different data paths for your vision versus your language versus different kinds of vision tokens. And so you kind of have to split those out into more metrics. This is also not supported in GuideLM yet. It's supposed to be coming soon. That's pretty much it. Well, hand it back off to Ashish, who will bring us home.
All right, thanks, Sam. So yeah, let's just wrap it up. So what we showed you earlier was to use the Fedora project to start your benchmarking journey. You can launch an instance in AWS with the right Fedora AMI going from the Fedora project website. Installing the NVIDIA stack, as we showed you, is pretty trivial. You just enable the right repos and install a couple of packages, and you are ready to go. You can use Podman to launch your VLLM server with the right model, and also launch Guide LLM container using Podman for good isolation on the system. But you have to pay attention to some of the small details as we showed you earlier. And then we recommend using Guide LLM. That's a tool coming out of from our team. It's a community project, so we have a link to the repo right here. So do go and check it out. You can use it to run your benchmark. It's trivial to actually run the benchmark, but as Sam had shown you, making sense of some of the metrics is a little bit more nuanced. And finally, I want to give a shout out to LLMD, the distributed inference project. And LLM inference benchmarking is a rich space to explore, especially with LLMD at scale. A lot of interesting scenarios there to explore using our benchmarking techniques. With that, thank you very, very much for attending. We are open to questions now.
Very non-technical question. So out here, we are trying to build a benchmark VLMs, right? So I saw you, for isolation, I get it, but is there any real incentive in using Podman or any other like Docker or containers? I mean, that's not my, my focus is different.
Sorry, to run VLM or to run
Yeah,
the
to
benchmark?
run the VLM benchmarks.
Oh, the benchmark part.
Yes.
The main incentive from our side is that it gives you an environment that is similar to the development environment for GuideLM. We do have one of the problems with building like a high-performance benchmarking tool is you start to run into issues with even like just Python itself having bugs with that reduce your performance. So it's good to keep that constraint of your entire environment is locked to some version, and you don't have to worry about pulling in the right versions of all of the packages. Yeah, I think generally we don't see. I mean, it's one level virtualization. We don't see a ton of overhead. I've never actually tested that, but I've seen tests for overhead of containers, and these days it's pretty minimal usually. We're mostly working within the CPU and in memory.
Not a question. I just wanted to ask if the slides are uploaded to the portal. Like, there's a lot of good information out there, and it would take me weeks to compile this together. And so,
Yeah, they're not at this point, but yeah, we will after the talk.